Okay, good morning, all of you. In today's video, we would be talking about diffusion capacitance. A PN junction diode, generally in case of forward bias, this diffusion capacitance is the dominant uh, factor. In case of reverse bias, we have depletion capacitance, depletion capacitance or transition capacitance. This topic I had already covered in last video. If you have not gone through it, you should go through it, okay, before actually covering this diffusion capacitance. Anyway, in case of forward bias, what happens is that there is no, and hence actually diffusion capacitance is the dominant capacitance that exists in forward bias, okay, in a PN junction diode. To understand diffusion capacitance, you must understand what's happening inside the PN junction with slight forward bias, right? So if you have a PN junction where P side is doped with Na acceptor atoms per centimeter cube and N side is doped with Nd donor atoms per centimeter cube. If you see the uh, charge distribution or the carrier distribution, let's assume this is x is equal to 0. Of course, in case of forward bias, this junction will be reduced, okay. Let's assume this is your xn and this side is your xp. So this is your xn and xp. In p side, of course, the majority carriers are whole and that will be equal to na. And if you see if you assume that v is equal to 0 right now, then of course n is equal to ni square divided by, so let's say use subscript p for denoting that we are talking in p side, and 0 that we are talking at forward bias is equal to 0, okay, or the thermal equilibrium. There is no voltage applied between p and n side. And if it is on the n side, a similar statement you can have that n is equal to nd and p is equal to ni square divided by nd, right? So let's represent it with the dotted line. So p is the minority carrier on the n side, so write it n0 and nn0. Now they are following the mass action law, that is np is equal to, however, when the junction will be slightly forward biased, let's assume with voltage VA, then in that case, the if you see the Fermi levels, okay, Fermi levels will be something like this. So now the Fermi levels, they will be separated by VA, okay, Q into VA. So Fn and EFP. In the junction region, because the Fermi levels are separated by QVA, now this mass action Np is equal to Ni square is not, will not exist, because there is an external force, external bias, right, which is deliberately trying to separate or maintain this difference in the Fermi levels. Now the mass action law over here, that changes to P is equal to Ni square into e to the power Va upon Kt, or sorry, Va upon Vt, Kt upon Q. So this will be the mass action in the range where actually these Fermi levels are actually separated. This is your Xn, this is X. Now to understand that what would be the exactly, so here you can find that if in case of bias in this region, okay, especially in the junction region, you must have P is equal to Ni square upon N into e to the power Va upon Vt. This should also hold for x is equal to xn and x is equal to xp, and that means the minority carrier on the p side, on the n side, that will not be exactly equal to pn0, but p at xn, that must be equal to ni square divided by n at xn. So n at xn is not going to change because this is the majority carriers, and we are assuming that uh, this is not changing much. So that is called the low level injection. Low level injection. And in that, we can assume that because this majority carrier is almost like a buffer stage and it is not going to change. So you can write it directly ND e to the power Va upon Vt. Directly you should write. So the actual hole concentration will be quite higher than, and this Ni square by Nd is nothing but Pn0 e to the power V upon Kt, right? So Pn0 is Ni square by Nd. That means there will be an extra charge over here. Now after once the charge has diffused, so from where this extra charge has come, because in case of forward bias, more holes are being diffused on the N side. A similar story is also for the N, that more electrons are being diffused on the N side. So that might be something like this. After this, so this can be N at XP, and this is P at XL. Now as it will go further away from the junction, because there are extra holes, right, in this region, they will try to maintain Np is equal to Ni square in the quasi-neutral region. Why? Because the separation of the Fermi level, okay, or all the electric fields that was appearing across the junction, and this region, the quasi-neutral region, that is not having any electric field, and hence they should obey the Np is equal to Ni square. Just to maintain this, a lot of recombination will start happening, and depending on the recombination lifetime, tau p on this side and tau n on the other side. Okay, so they will try to recombine, and as you go in the quasi-neutral region, the concentration of holes that will reduce, and if you go very far away from the junction, this will finally go to np0, and it will maintain this equation, mass action law. Okay, np is equal to Ni square. Now this profile is defined by the recombination time or recombination length, okay, or diffusion length Lp, where tau p is related as tau p is equal to Yeah, LP square divided by dp. This is how they are related. Or LP square is equal to dp into tau p, where dp is the diffusion constant that we all know. Now, having said that, you can find that what is the profile. So px in general, instead of writing now at xn, I just want to write a profile for the minority carriers in inside in n-type material. So that will be equal to pn0 e to the power va upon vt into e to the power minus x minus xn upon lp. So this profile is exponentially decreasing. Okay, e to the power minus x upon lp, something like this. Because I have just used minus xn, you can also remove it if you want. All these x are actually taken from x minus xn. So this origin has shifted xn. So before that, you should also actually write delta p, right? So what is the excess carrier that is going inside? If you want, okay, what is the excess carrier? So this was the case np0 in when v was 0, right? So as you are applying v, the excess carriers are subtracted. You can just subtract pn0 from that. So one stage over here, delta pn is equal to pn naught into e to the power v upon v minus 1, that you should write. Okay, so now as a function of x, you have this expression. A similar expression you will get for n also. Delta n minus, okay, x plus xp, technically right, just shift the origin to xp now. Okay, on this side, and you will find it is equal to np0 e to the power va upon vt minus 1 to e to the power minus, technically it will be plus. Okay, anyway, so x upon ln. So these are the extra carriers over here. Now if you want to find the, okay, so now let me draw it over here. So this was your pn0, this was np0. You have a profile like this, px, delta px and delta nx. Why we are not interested in the majority carriers? Okay, so n or p, majority carriers we are not interested because that is constant. Okay, and in capacitance we are generally interested in del q by del v, right, by definition. And hence, because these charges are almost like constant, and so we should focus on minority carriers only. That's why the majority carriers are not being taken. Now you can find that there is an extra charge over here. If you see on the, so you just integrate this function delta p charge, right? So total charge in the system, if you want, you add both of them, right? Is equal to qp plus qn So let's find the QP first. QP is equal to E into delta P x integral from xn to infinity, right, dx. If you see, so this is your xn and just integrate it to infinity, and that you can write. So from this expression, okay, so in this expression, whatever is not dependent on x, you can just take it out. So E into Pn naught e to the power Va upon Vt minus 1 integral from minus xn to infinity e to the power x minus xn upon Lp. Of course, when you will integrate, this integral will count as total area of Lp. Okay, just you can do it. So Qp, that is equal to E into Lp into Pn naught e to the power Va upon Vt. Likewise, Qn you can calculate as E into Ln into Np naught e to the power Va upon Vt minus 1. So total charge Q, you have got EL Pn naught plus ELN Np naught, okay, e to the power Va upon Vt minus 1. So now you can find the C diffusion capacitance very easily. Del Q by del Va, that is equal to ELP Pn naught plus ELN Np naught divided by Vt into e to the power Pa upon Vt. So that is your diffusion capacitance. This is the expression. And if you remember, that is related with diode current. Because in diode current, okay, one more thing, that this diffusion capacitance is per unit, because we had not taken area into consideration. Okay, so all these expressions that must be multiplied by, so A. So this QP is actually per unit area, per unit area. So whatever is the cross section of the junction, you must multiply with them. So the final answer we are getting, that is capacitance per unit area. And if you know the expression for this diode current, J D is equal to Js e to the power Va upon T minus 1, that is the diode current. Js is given as, that is reverse saturation current density, that is equal to E dp Pn naught divided by Lp and plus E d Np naught divided by Ln. So this was your reverse saturation current density, and this is the diffusion capacitance density. Can you find any relation between them? Yeah, right. So you can see these two expressions are related with, because there is another equation, that is Lp square is equal to dp into tau p. So that is how the diffusion length is defined, where tau p is the recombination rate, recombination life. Tau p is the recombination lifetime of holes. Likewise, dn ln is equal to dn tau n. Now, if you just compare them, here actually LP is in multiplication, here LP is in division. So you can write it as C diffusion is nothing but equal to Js, okay, multiplied by, if you just multiply it with tau p, okay, and tau p is equal to LP square upon dp. If you multiply with this factor, we will get exactly this expression, right? So you can write it as Js tau p, not only tau p, but actually it will be uh, yeah. So depending on the majority carrier currents, you can, sorry, you can write it as E. So one of them that will be actually the majority, mainly dominant, okay, depending on Na or Nd, Pn node or Np node. So that will decide the diffusion capacitance in general, but you can write it as Js into tau lifetime of the carrier, or effective lifetime you can say, into e to the power Va upon Vt, right? So why I am not writing tau n or tau p, or just write E effective? So that will be dependent on tau n and tau p, okay, and that will be, because here you have to multiply with tau p, here you have to multiply with tau n, then only you will get this expression. So C diffusion can be written as, now do you understand this? In case of forward bias with 4.1 volts, you can find that this minus one term can be neglected, and JD, diode current density, that can be written as equal to Js e to the power Va upon, right? And that is why you can see diffusion is equal to current density multiplied by tau divided by, okay, so divide by Vt, there should be, yeah, so this divide by Vt, so that we were neglected, so this should be divided by Vt. This is your final expression for diffusion capacitance. We can see that, or in terms of current, you can write C diffusion per unit area. This was per unit area. C diffusion is equal to ID into tau effective, sorry, tau effective divided by Vt. So as you increase the diode current, this diffusion capacitance is increasing. And how, what is the relation on Va? Exponentially it is increasing. So if you draw it, you will find that diffusion capacitance is going like this, okay, e to the power Va upon Vt, right? Let's say it is C. So this is your C diffusion. Here you have applied diode voltage. So in forward bias, diffusion capacitance that actually dominates, and in case of reverse bias, we have already seen that it is depletion capacitance, right? So this was going something like this. So the overall capacitance, if you just try to plot, that will go like that, will follow depletion capacitance up to this point, and then it will be, so this is your C total, C diode. This was your diffusion capacitance. Sorry, depletion capacitance, C depletion. In reverse bias, depletion capacitance is the dominant factor. In forward bias, diffusion capacitance is the main factor which affects, and here you have the total capacitance curve that would look like this. Now you can see that the capacitance of diode is more in case of forward bias as compared to reverse bias. In reverse bias, might not be visible one day. So in reverse bias, you can see that as you increase reverse bias, the capacitance decreases, and we had also seen that C depletion capacitance is proportional to 1 by root function. In general, it is C depletion is proportional to 1 by plus VR to the power 1 by L, right? Where in case of abrupt junction, this M is equal to 2. In case of linearly graded junction, this M is equal to 3. And that is why when we are talking about the transient time of diode, transient time, it is the forward bias current that is more important. That is more important. And we try to overcome this when you are going from reverse bias to forward bias, because the capacitance was small, so the time required will be small. However, if you are going from a forward bias to reverse bias, the recovery time, okay, T required, that will be large because of large forward, or you can say that this diffusion current, diffusion charge that has been stored on the other side. To make it reverse bias, you must flush all these charges on in this side and this charges on this side, and that takes time. And that is why when we are discussing the recovery time of a diode, that means switching time, generally we consider forward bias to reverse bias and not reverse bias to forward bias, okay, because this is already small. Okay, if we can design our diode for this forward bias to reverse bias criteria, of course it will be satisfying this condition. So this reverse recovery time generally dependent on C diffusion, okay, and generally we talk it in terms of uh, forward bias to reverse bias condition. So when the junction was forward biased, a lot of charges were there on the N and P side, extra minority charges that has to be shuffled or removed so that it can be brought into reverse bias condition. That is the topic of next video. Okay, so I will discuss it. Till then, you can actually go through some reference books also and find it. Thank you.